So I want to start by showing you a quick video. This was put out by the Chinese Academy of Sciences. They do these really slow motion reaction videography, which is pretty interesting to watch. So this is the formation of lead iodide. So this is a lead nitrate solution. In this the drop that's being added is potassium iodide. You can see sort of the instantaneous formation of this yellow compound, which is a solid, which is PbI2, lead iodide. So I have the equilibrium expression written up here for lead iodide dissolution. So here's the solubility product, or Ksp, the solubility of lead iodide, this yellow compound, which you can see is pretty small. So you know, the concentration of lead 2 minus times the iodide squared gives you this really tiny value, which if we're only considering this reaction between lead 2 plus and iodide as the only type of reaction between those two ions, then what we would expect, you know, sort of from an observational perspective, is that as the concentration of the iodide component increases via, say, the common ion effect, so you keep adding, say, potassium iodide to solution, that's going to continue to drive down the lead concentration as it continues to satisfy that constant Ksp. And what we observe is that to be true when we're starting at low concentrations of iodide and moving towards progressively higher concentrations. So what I'm showing you on the right is what's called a log-log plot, where we have the log concentration of lead on the y-axis. So this is concentration of lead, and these are you know, minus values. So these are essentially 10 to the minus in molarity. That's what the log plot or the log scale means here. And on the x-axis we have the concentration of the iodide ion. So again, these are like 10 to these values in terms of molarity. So down here we would have, you know, at 10 to the minus 3, that's the same as like 1 millimolar. Then 10 to the minus 2 is 10 millimolar. Then all the way up to 1 millimolar, or I'm sorry, 100 millimolar, and then up, continuing up from there. So what we do observe here is as the concentration of iodide increases from the very low end over here and we move this direction, what we see, these blue dots, are that the concentration of lead here continues to go down in this sort of log-log linear way, as we would expect from the sort of linear concentration dependence on lead here. But what we observe is this sort of threshold that where we sort of have this asymptote where as you keep adding more and more iodide at higher and higher concentration of iodide, when you get to the value of 10 to the 0, which would be 1 molar, this we start to increase the concentration of lead in solution, and that goes up. So what's going on here? So we have to think about really the chemistry that's occurring when something like lead 2 plus and iodide form. And several of you may have taken an inorganic chemistry course like Chem 275. If you haven't, it's not a big deal. What you'll learn in that class is that ions often, when they react with metals like this, the metals are going to act as a Lewis acid, and they are going to accept a pair of electrons, and the ions here, the negative ions, are going to act as a Lewis base, and they are going to donate a pair of electrons. And they're going to do that stepwise. So if one lead 2 plus ion reacts with one iodide ion, it's going to form this new complex, which we call an adduct, or a coordinate compound, where you have one lead and one iodide, which yields an overall positive 1 charge. So this would be an aqueous complex. And then you could imagine the next step in this formation would be that you have lead I plus another iodide that proceeds to make the next step here, which could be a solid, but you also see this could be an actual soluble compound, neutral compound. And what's new for you likely is that this process keeps going because lead can accept multiple donors, not just two to form the neutral complex. In terms of bonding, it can take 3, even 4 iodides that surround it in solution as it's competing with water as the hydration sphere. So we could have lead I2 plus another iodide and make this new adduct, lead I3, and now this overall complex has a minus, and that lead I3, as I said, can add up to one more lead or iodide to make lead I4, 2 minus, again, aqueous. Each one of these reactions is its own, achieves its own equilibrium based on whatever the free energy change for that reaction is and its relationship to the equilibrium constant K. So each one of these is going to have a K associated with it. And we call these stepwise formation constants, where we add one, what we call ligand, or iodide ion, in this case is the ligand, to that complex each time. And all of those Ks are working together. They're all related to each other because, say, the first K here is a function of iodide, but the second K is a function of iodide, and the next K is a function of iodide. The iodide concentration in the solution is only one value. You can only have one value for a concentration in a beaker, right? But all of these equilibria simultaneously are depending on that iodide concentration. And what happens, as you see, is that at lower concentrations, the lead ion concentration is largely dictated by the Ksp formation because of this very low value. But as that and as we increase the iodide concentration, we keep suppressing or decreasing the lead 2 plus, essentially from the common ion effect, which is what this plot is telling you. But as we sort of reach this threshold, what happens is these stepwise complex ion formations of more complex lead iodide start to take hold, and in doing so, they start to push these equilibria to the right, because you are increasing the concentration of the iodide, and by doing that, that has to push this whole equilibrium to the right to get rid of that iodide. In doing so, it's going to create more of this complex, the lead I2, which means it's going to use up and sort of free up or liberate some of the lead I plus on the left side. And that's why you sort of have this complex interrelationship between all of the equilibria that depend on lead and iodide. And in fact, we'll talk about in Chapter 8, this is a pretty simple system, and that many metal ions actually may behave in this way with one ion, but they may behave this way for all ions. So if you have a natural water system that contains not just iodide, but bromide and chloride and nitrate and sulfate and phosphate, those metal ions may be participating in multiple complex ionic equilibria with each one of those ions, meaning the actual concentration of the metal ion is highly regulated by a whole set of different competing equilibria. In natural waters, the number of equilibria governing one single metal ion concentration can be in excess of 100. And so that's really the big step we're going to be making in Chem 241, is moving away from just considering a single ionic equilibrium, say from the perspective of Ksp, and starting to consider that water is much more complicated, and we can't just isolate a single reaction to compute concentrations. We have to consider it all, and that's going to be the focus of the treatment of systematic equilibria in Chapter 8. So I just pasted in several of the actual reactions here that I mentioned before, but you can see that these are written slightly differently. So there's two different ways to write these complex ionic reactions. One would be in the stepwise way, which I just walked you through in the previous slide, where you are iteratively adding one iodide ion to each complex each time, and we could write out an equilibrium constant for that, or we could write it as what we call a beta value, which is a complex formation. It's the same, it's an equilibrium constant, but the beta tells us specifically that we're referring to the formation of that complex in one step. So for example, in this second step, we go from lead-2 plus 2 iodides to form the aqueous species. In this third step, we go from lead-2 plus 3 iodides all in one step to form lead iodide I3 minus. And so those would be, you can compute these betas if you have the original stepwise Ks, because we know that we would essentially just combine those reactions together. Whenever you add two equilibrium reactions together, you multiply the Ks, and that's how the betas are derived in this case. We're not going to spend and belabor this too much. I just want to give you a big picture idea of this, which is going to segue nicely into Chapter 8, that things are more complicated than we think. So the last thing I'm going to do is just let's think about a real example. So again, this comes from your textbook. So I'm just going to walk you through this example briefly. So the question says find the concentrations of lead iodide plus lead iodide aqueous, which I want to say lead iodide aqueous is distinctly different than lead iodide solid, even though they have the same stoichiometry, one lead and two iodides. There are two versions of this complex, one that precipitates and one that's actually solubilized by water, and that's very common, that some even neutral complexes can still be soluble in water to some degree, which is going to be governed again by delta G and ultimately dictated by the equilibrium constant K. So we're trying to find the concentrations of three of the complexes, so we're looking for this one, we're looking for this one, and we're looking for this one. And we're looking for those under saturation conditions where lead iodide is fully saturated, meaning it's not going to dissolve anymore, so we're at equilibrium, but we're at equilibrium with different conditions or different concentrations of the iodide concentration. So since we know we're in a saturated solution, then we can start with the Ksp expression, which is this first one, which tells us what the solubility of lead will be under those conditions. And so the first step, the Ksp expression is rearranged to solve for lead concentration, because we know that the iodide concentration is fixed at 0.0010. This is the Ksp here, 7.9 times 10 to the minus 9, so we can solve for a lead concentration of 7.9 times 10 to the minus 3 molar. Okay, so what does that mean? Well, one thing you have to consider, and I sort of alluded to this, is that all of these reactions here that I have, they're all true simultaneously. Mathematically, they all have to be solvable. And the lead concentration, if we use one equilibrium expression to compute the lead concentration, that is the lead concentration in the solution, which means that lead concentration has to also satisfy all of the other simultaneous equilibria. It can't be one concentration computed from one equilibrium and another concentration computed from the other. So, and we'll see that here in a second. So let's say at 0.0010, which is the concentration of lead iodide, that's the same as 10 to the minus 3, which would be this concentration on our log-log plot. So this is the same as 0.001 molar iodide. And so each of these lines that are intersecting are the solubilities or the concentrations of each of these complexes respectively. And we're going to do this in class. We're going to do this with Flint water, and we'll compute something very similar, but more complicated than this. So if you follow any one of these lines, and you could compute exactly what the concentration of that complex would be under any conditions of lead or of iodide concentration. And so in this case, we are thinking about 0.001 molar So I'll just draw a line that's, sort of roughly tracing this. And anytime this vertical red line intersects one of those black lines denoting the concentration of any complex, that would be the concentration of that complex at that iodide concentration. So each one of these lines is essentially the solution to each one of these expressions over all possible iodide concentration ranges. So you can see the power and the utility in software modeling, where we'll do this in this class, because doing this all by hand is a huge pain, especially if you're looking at a large range. But we can compare our first number, right? We computed it using the Ksp equilibrium, but we could have computed it just as easily using this value if we would have known what the concentration of lead iodide plus was, but we didn't. So the only one of this set of equilibria that really worked well would have been this the first expression, because we knew Ksp and we knew iodide. That tells us our lead concentration is somewhere in this region, right? And that's pretty consistent with the value we computed, which is in the roughly 7.9 times 10 to the minus 3 molar range for lead. So we can move down and we could compute our lead iodide plus by doing the same process, right? We know iodide. The iodide concentration can't change. It's fixed across the system. So that means the iodide concentration can be input into any one of these expressions, and we can back out the concentration of any of the others, knowing that we also just computed the lead concentration for each of these. So now that we have both the lead and the iodide, we can compute then what the equilibrium concentration for each of the complexes would be. And that's what this first step is. So we take the lead concentration, we toss that in right there. We take the iodide concentration, we toss it in there, and we use the first K1, which is the 1.0 times 10 to the second, which just comes from down here. It's computed as that. And that gives us a value of 7.9 times 10 to the minus 4 for the PBI plus, and so that's somewhere in this region, so it's just past the minus 3 range into the minus 4 range. Then we could do the same thing for each one of these. So that's all at 0.0010. Now let's just so you essentially plug and play, and you'll get values that are pretty consistent with this modeled equilibrium plot, the log-log plot. If we jump down to the 1 molar case, which is part B, 1 molar is the same as 10 to the 0 here. So I'll try to draw a straight line as much as I can. It's kind of hard in PowerPoint, harder than other programs. What changes? Well, we can go back and compute our lead 2 plus concentration. How did we do that? Well, we just reevaluate our Ksp expression, but now the iodide, instead of being 0.001, just becomes 1, and that gives us a lead concentration in the 10 to the minus 9 range, which, if we were to look at the intersection of this red line, this line that's moving down this way, that's free lead 2 plus, it's the lead 2 ion. You can see that's intersecting down here in the minus 9 range, below where the scale cuts off at minus 8, so that's consistent. So the lead ion concentration is actually going down, but what the blue line is telling us is lead total. What's the difference? Well, lead total is the total amount of lead that's in the system, that's solubilized in the system, that's not a solid. And so what that's telling us is that past this sort of point right here, where we're precipitating out a bunch of solid, that's the maximum, where we've precipitated out the maximum amount of lead iodide as a solid. Now as we push the iodide system this way, the equilibria of all of the complex lead formation starts to kick in, and we start to dissolve the lead 2 or lead iodide solid, because we start to push the equilibrium to the right for all of these formation constants down here. And by doing that, we start to dissolve the lead iodide. And the reason why, if you can see that, is as these 4 let me do this in a different color. As these four that I have highlighted in green down here, all these complex ion formation constants, as the iodide concentration starts to go up, that shoves the equilibrium to the right for all of these, right? Because the Le Chatelier's principle says, well, if you've got more reactants, then it's going to push the equilibrium to the right to use up those reactants to get it back to equilibrium. But in doing that, you can see even at the in all four of these cases, by pushing the equilibrium to the right, it's using up lead 2+ in each one of those reactions. By using up that lead 2+, it's decreasing the lead in the system, which is the same lead that is in the original Ksp expression. So that goes down, and if that goes down, then this equilibrium also shifts to the right, which means we have less PbI2, or lead iodide solid, in the system. It starts to continue to dissolve because this equilibrium here is no longer satisfied, because the lead 2 starts to get depleted because it's used up in these other subsequent complexation reactions. And that's why we start to see this go up. Even though the lead 2+ is going down, we start to liberate more lead from the solid, which in terms of it gets converted into all of these complexes. So the total amount of lead that's dissolved in solution, which would be the sum of all of the concentrations of all the lead complexes plus the lead ion, starts to increase. So this is sort of an illustrative process for the fact that we can't, and often are not, relegated simply to anions being added to cations and ending at the neutral compound. Because if we keep adding ligands or more of the anions, often we can push the equilibrium to redissolve this. And this is a pretty effective tool. This happens often with hydroxide ions, because hydroxide is just another anion. And so many, including lead, many metals will react with hydroxide to obtain, say, an equilibrium like lead hydroxide, which is solid as a neutral compound. But if we keep then increasing the hydroxide concentration, then we will start to see an effect like this, where we start to then resolubilize the lead because we start to make lead hydroxide 3 with a minus, lead hydroxide 4, etc. And we'll talk about that as we talk about the Flint, Michigan example too.